Today we're going to be looking at engineering stress strain. So how to calculate it, how to plot the resulting curve, and then how to get four quantities: elastic or Young's modulus, yield strength, tensile strength, and ductility. And so I'm going to go through how to calculate and determine these things, and then go through and work an example of a metallic sample, how to do this. So let's start with how do we get engineering strain? So engineering strain, or this epsilon here, is the instantaneous length of our sample minus the original length of our sample divided by the original length. So that's Li, L naught, or 0, and that is the same as the delta L, or difference of length, divided by the original. So what this looks like on our sample, so this is our original dog bone sample. We have a gauge length, so this is within the reduced section. So this can be standardized to be about an inch or two, but anywhere in the reduced section, we have this gauge length that I'll call L naught. So we measure that originally, and then at any time point during the test that we've applied force, that you can see by these red arrows, so that's the tensile axis, up and down. And so at any time point, we can measure the length of that sample, and that is the instantaneous length. So we have that here. So during the test, we're not measuring this property. We're not going in with calipers and measuring the length at any given time point. We're relying on the test sample, the test material, the test machine, like an Instron or other tensile tester, to calculate what this delta is, and then we calculate epsilon from that. So we'll go through this in the example. So engineering stress, how do we calculate this? So our equation here, sigma, this is engineering stress, and it is the tensile force that we just saw with the red arrows divided by the original cross-sectional area. So sigma is engineering stress, F is the applied tensile force, and A is the cross-sectional area. So if we go back to our sample like this is kind of a side view of our sample. So if we look at and take some fragment in the reduced section, denoted by this red line, we have our cross sections over here. We can typically have one of two, but this isn't the only type of cross section, but we're going to look at rectangular and circular. So for a rectangular, I'm going to call this long distance the width. So essentially that's the width here. And then the thickness is how thick it is into the plane of the computer. So that could be one. We could also have a circular cross section with a radius r. So either one of these, we can easily calculate the cross-sectional area by the area of a rectangle, so W times T, or the area of a circle, so pi times r squared. So this are two easy ways we can get this original cross-sectional area. And again, since it's the original, we don't have to do this during the test in most cases. We can just rely on the original cross-sectional area and then the force at any given time point. Right. So we're back here with an example and some tensile data. So this is data collected on an Instron universal testing frame, and we have I've inserted the dimensions that were recorded by calipers up here, and then this is the raw data that the machine has given us. So this was one of many tests, but we're just going to look at one. And so it gives us time displacement, which is another way of saying the difference in length. We have force, and we have tensile strain. So you might have seen from one of my previous videos, but this tensile strain is from what's called an extensometer. So this gives us a better measure of the displacement just from that gauge length that we talked about. So I'm going to be using this term. So a little bit about this sample, if you want to know what this sample is. This is a 4140 steel. So this is a alloy steel 4000 series with 0.4% carbon, weight percent carbon. This is used for bicycle frames and so forth. It's very strong, even though, and so we can use a less of it. So it's got a good strength to weight ratio. And what this has been how this has been processed is we took this, we heated it up, formed austenite, and then quenched it, and then we tempered it at 200 degrees Celsius. So that's kind of the process. Not really important for the purposes of this video, just in case you want to know a little bit more about it. So this is the data that we're going to be working with. And step one, what we're trying to get here is the engineering stress and strain, or strain and stress. So that's what we're going to start with. And so here I'm going to just type in engineering strain. That's the first thing we're going to look at. In the format of this file, I just have the units in the second. So we're going to call this millimeters over millimeters, but this is unitless because it's a millimeter over millimeter. So you don't technically need any units. So if you remember back to our equations, this was the instantaneous length minus the original over the original length. And that difference in length was a delta, and that is actually the displacement, or it's this, the whole thing is actually this strain. So this strain is actually already calculated for us, but I'm going to kind of show you two ways here. So like, let's say if you don't have the tensile, if you don't have the extensometer data and you only have displacement, or the delta L, then what you're going to do is you're going to take this and divide by the original gauge length, right? So this is, I'm going to call this without the extensometer. So that's how you do it. And then we just click here on the box. Oop, I forgot one thing here. So when you're doing this, you always want to put dollar signs here so that initial gauge length doesn't change. And then do that again, and it should look good now. All right, so that was without the extensometer. With the extensometer, so I'm going to do the engineering strain again, and the same units, unitless. And all that's going to be here is this. So this is actually just going to give us our strain, because what it's already done is it's already taken the original gauge length and essentially divided it by the displacement that it has. So all we have to do is just get it consistent, and since this is a percent, we just want to divide by 100. So that's all I'm going to do for this one, right? But all you're going to do, depending on what kind of data you have, you'll either take the displacement, which is the delta L, or you might have the strain directly. So this would be with the extensometer. All right. So then we get to the engineering stress. So this is going to have, the most common units are going to be megapascals. So that's what I'm going to work with. And it always tries to correct that. So MPa, so megapascals. So that's what we're going to calculate here. So remember, this is the force divided by the original cross-sectional area. So what I'm going to do is I'm going to take the force, which is this one. And so this is in, you'll note over here, kilonewton. So I actually want this to be in newtons, right? So if I want to do that, then I'm going to multiply by 1,000. So I'm going to go ahead and convert those units just so that's in newtons. And then I'm going to divide by the cross-sectional area. So up here, you'll note that I have thickness and width. So again, this implies that we have that rectangular cross-section. So that's what we're going to use in this case. And so all we have to do is multiply these two by one another to get the area of a rectangular. So that's what I'm going to do here. And one thing as I'm doing this, I also want to keep these set. So use the dollar signs again. So that's not going to change at all because it's the original. And so I'm multiplying those two. So it's important to keep track of the units here because I had kilonewtons, I converted to newtons, and then I divided by millimeters squared. So normally what you would want to do is I would recommend is convert everything to kind of base units. So that would be, newtons here, meters here, and that would give you a Pascal. I would recommend going through the units on that if you're not familiar. However, there's a shortcut, and it's one that a lot of people that work with metallic samples will be familiar with, because megapascal is the same as a Newton divided by millimeter squared. So that's why I'm keeping this and I'm not worrying about the units, because that millimeter squared will actually give us megapascal. So it's kind of a shortcut, but if you don't trust that, definitely recommend going through the unit conversion and checking for yourself. All right, so then I'll extend this down and I should have engineering stress strain. So I'm going to plot this. And again, I want to use the extensometer because I have access to it and it gives us better elastic data. And so I'm only going to use those. I'm not going to deal with the displacement version. I'm just going to deal with these two. So I'm going to highlight these two, extend this. Oop, that's not correct. I clicked the wrong arrow. All right, so I'm going to do that again. So let's highlight this first two, and I'm going to do Shift Command down instead of over. That's on a Mac here, so it's I believe Control Alt down on a PC, and so that highlights all of them. And then I'm going to come up here to Insert, and I'm going to go to a Scatter. And because we have a lot of data points, we don't need to use the scatter. We don't need to use individual data points. So I instead just use scatter with straight lines is what I prefer for this type of data. And that's what we have here. So this gives us our plot. And so this is, just label this engineering stress strain. We can do a little formatting here. We can just get some of these quick formats aren't too bad. So let's try this one here. Nope, we don't want the fit yet. We don't want to do that. So this is going to be down here. This is engineering strain. And again, you don't have to put units, but just out of habit, I like to put millimeters over millimeters. And then engineering stress. And that's, again, megapascal. All right. So, and then this is our only series, so I'll get rid of it. All right. So that is the first part done. We have the engineering stress strain curve for this 4140 steel. And we have it plotted. So again, this plot is the kind of foundation for a lot of properties that we have. And so we're going to go through and look at those four quantities. We're going to determine the elastic modulus, we're going to determine the yield strength, tensile strength, and finally ductility. So one last note before we sort of shift over and look at the elastic modulus, I'll note this little blip that we have here. So if you've seen some of my other videos, you might have already seen this, but this is a blip because in our specific setup, when we use the extensometer, this is a physical device that you don't want on when it breaks. And so we have it take off the extensometer, or we have it stop the test so that we can take it off. So the machine stops, we take off the extensometer, and then it continues the test with just the displacement data from the crosshead. And so that little hiccup is the stopping of the test and kind of the recovery. So this actually tells us a little bit about the elastic recovery or the lack of viscoelastic properties that this material has. But you can see it pretty much goes away. So if we really wanted to, we could get rid of that data because we know that it's just from the removal of the extensometer. But I'm going to keep it just for these purposes. But just keep in mind, if you see this blip, that's what it's for. So now we're going to get into the different quantities that we can obtain from the engineering stress strain curve. So we've already plotted it. We've calculated the engineering stress and strain. And so now we're going to look at these terms. And the first one is the elastic or Young's modulus. So I use these interchangeably, but some people in some books will refer this specifically as the Young's modulus, but they are the same thing. So if we have an engineering stress strain curve for a typical metal like this one down here, our equation for elastic or Young's modulus is the engineering stress over the strain. But it's not quite that simple because this is the elastic modulus. So it's only for the elastic portion of the curve. And so what we want to do is we want to look at this curve and isolate the elastic portion. And how we can do that is typically by the linear portion early on versus the nonlinear portion after. And so this red dashed line is roughly that indication for us. And so before that is the elastic, and after that is the plastic. So we only want to deal with this very small region, and we want the stress over strain, or another way of saying that is it's the slope. So the the elastic modulus is the slope of the linear elastic portion, because again, this is the expression here, and this is derived from Hooke's law, which is a linear elastic model. And so we're only looking at this elastic linear portion. So we're going to take, to calculate this term then, we're going to isolate the elastic portion, and then we're going to find the slope of that region. So we're back here, and I want to go through how to calculate the elastic modulus. And if you'll recall, the elastic modulus was the slope of the linear elastic portion. And for this particular graph, you might notice that it actually has a pretty good gradual transition region, right? It looks like it actually starts to gradually transition through a whole host of things. And so, excuse me. So because of that, we're going to probably focus on some of the early curve to be able to get our linear fit. And so what I'm going to do is I'm going to shift this over, and we're going to do this just for we're going to focus on the linear portion. And so I'm going to have engineering stress strain again, and I'm just going to look at the linear portion. And so I'm actually just going to take it till about 1,000. And so what I'll do is I'll just do this again, just so I don't mess with that original data. So I'm just basically copying the data. And since I start to see, I can't really tell where the gradual transition between linear and nonlinear is, I'm going to take it around 1,000. So this should give us more than enough data points to get a nice fit. And so what I'm going to do is so this is 1,000 on the y-axis of the stress. So I'm just going to go down here until I see 1,000. Scroll down. And right here, it's a somewhat arbitrary point, but I'm going to just take those. And so again, I'm just going to do the shift command down, and I'm just going to hit the delete button to get rid of that. So now I'm going to replot, or I'm going to plot a different version. So I'm just going to select this data now, insert another plot, just like we did before, and move this down here, right? So you can see this is actually pretty linear. Maybe it's a little, you might be able to see a little touch here that's nonlinear, but this is actually a pretty good linear region. So all I have to do is have Excel do what it does best and do a linear fit. You can do this with formulas in the body here too, but I'm going to do that with the curve here. So I've selected my data, and I'm just going to right click, and you can add trend line. So Excel does these basic fits very well. And so I have linear here. So this is what we want, because we want to fit the linear elastic region. You can call it what you want, whatever. You can forecast and so forth. But I'm not going to mess with any of that. But what I will do is go down here and display the equation and display the R² value. So how good of a fit it is. And you can see here that this is what it's given us, right? So you can actually see the dotted line here, and I can change the color here, should be able to. Just make it so it's a little bit more visible maybe. So I'll change it to red. So the red curve, you can see it fits really well. You see a little separation here and there. And then really the only difference you see is maybe up here towards the top. And so this could be where that just starts to downward slope towards the plastic region. But in general, 0.9991 is a very good R-squared value. This is really good fit. And so we're going to be really happy with that. And so the equation is here. And again, I could make this a little bit bigger. This is our linear fit for this slope and for this region. And so we don't necessarily care about the y-intercept or anything. What we really care about is the slope, which is the mx of this part. So this number here. So 184,578. That is our value for that. Right, so I could go ahead and write that down. I could do that here, wherever we want to do it. But this is our 184,578. And again, this is going to be in megapascals. And again, just because I'm a perfectionist, I want to keep that there. So this is in megapascals. Most elastic moduli for metals are going to be in terms of gigapascals. So if we want to convert this, we can take this value and divide by 1,000, and this will give us the gigapascal. So our elastic modulus is 185, roughly, gigapascals for this material. And so we could look up and compare to known values, and we would see that this is actually pretty close. This steel tends to be about 207 gigapascals. So we're a little low, but we're actually very close to this value. So this is how we can get the elastic modulus. And I do want to put just one alternative out there. So if you don't want to go through so you'll notice that, we basically had to manually take this value from the slope that I did down here. So I just manually looked at it and wrote it here. If you don't want to do that, there's a slightly different way to do it as well. I would still recommend plotting so you can see how good of a fit. You can see if there's any differentiation between the two curves. But if you want to just get this value a little bit more conveniently, you can do a slope function. So if you do slope function, you'll see that it has known y's, known x's. So you can basically take all this data for the y's, go back up, comma, known x's, and then solve for that. And you'll see that we'll get the same thing. So you can do this directly with the slope function. But again, I would caution you, the number of times I've seen this where somebody just does that and they don't plot it and they don't look at it and they don't sort of determine whether this is a good fit or not. You can also do the r-squared. You can also use a function to get r-squared, but I would still recommend plotting it just so you can see what that looks like on an actual curve. So along with that, and how we can actually separate these two portions of the graph out, is the yield strength. So you'll notice that this point that we defined here that separates the elastic from the plastic is actually our yield strength, because that's the term and that's the strength at which we have noticeable plastic deformation. So for this type of curve where we have a gradual transition, so that's the one we're going to work on in the example. There are other types, but we'll focus on this gradual transition. We're going to use what's called the offset method. So our yield strength here is sigma y, y for yield, and we're going to determine that by what's called the 0.2% offset method. This is the convention for the US. There are slightly different percents in other countries, but I'm going to stick with this. The procedure would be the same for other offsets. So what we do is we have to determine the elastic modulus first, because we need that slope. And once we have that, we're going to make a line that's parallel to the elastic portion. But step two, we're going to offset that. So that line gets offset by 0.002 strain. So we're going to shift that over. And what we do is we look at the intersection between our offset line and our actual curve. So the red and the blue, and that happens right here. And so that is our defined yield strength where we have this intersection. So we would first want to determine the elastic modulus, and then only then can we do the offset after that. So we're going to do the yield strength first, or sorry, we're going to do the elastic modulus first. So we have that, and then we're going to determine the yield strength. So you do want to do those in the order that we've looked at. We're back here and we're going to do the yield strength. And again, we're going to do this with the offset method. We have just determined what the slope of the linear elastic portion is. So that is the elastic modulus, or Young's modulus. And we have the plot up here. So I'm going to do, because again, we want to do the offset. So I'm going to basically take these values that we see for the linear fit, and we're going to use that, because now what we're going to do is we're going to do offset. And so I'm just going to call this offset. So what we want to do is we want to take the y equals mx plus b, right? So we have the slope here multiplied by our x value, which is, and I'm going to go back to here. So not just the linear portion, but the whole thing. So I'm going to use this. And again, I don't want this slope to change. And then I'm going to add, and I didn't record this directly, but this is the 42.468. So that is effectively the slope of the linear elastic portion, right? So we are basically just plotting this slope. But again, I want to offset it. And so what I'm going to do, and there's multiple ways you can do this, but what I'm going to do is I'm actually just going to take and put parentheses around our x value and actually subtract that 0.002. So this will offset the values in that way. And so I'm going to extend this down. And so this is going to be my offset. And in this point, I actually want to plot this versus this. So this is our engineering stress, and this is our offset value. And I'm going to add that to the one up here just so we can see it. So let me go back up to my original plot, select data, add. So this is, I'm just going to go back and call this engineering. This new one is going to be called the offset. I want the original strain values, which is over here, and I want my offset values. So these are the y values, the stress values for the offset of the linear slope. So I'm going to do this. And you'll notice a lot of negative values there. That is fine. It might make our plot look less fun. Okay, here. So it might look a lot different, but that's just because we are plotting a lot more data than we actually need. And so if I double click on the y-axis, I just want to go back to 0 because anything negative doesn't matter. And you see it plots a lot of extra data. And so I'm going to get rid of that, or I'm just going to rearrange the y-axis. So it's just 2000. Let's actually make it a little 2500. All right, so there. So again, with this offset, you're plotting a lot of extra stuff that we don't need, but I just want to focus on this region so we can see the original curve, and the orange looks like it's our offset. So with that in mind, then, this gives us the ability to determine the yield strength, right? Because we have our original curve in blue, and we have our offset slope here as well. And all we want to do is look for the intersection. And so the most straightforward way I would say to get this is you can basically just do what I just did. And so let's zoom in, and I just want to focus on this intercept region. So let's zoom into about 1300, and then let's go to 1500. And you can see now it looks kind of funny on the x-axis. So let's go to that, click on that, and let's 0.02, and let's only go to 0.02. Let's see. Okay, so now we're getting a little closer. You can see we can just adjust this just so we can see a little bit better. We don't actually need a lot of this data. So all we're doing is manipulating the scale bars so we can see this intersection. And so here you can see, and we can just kind of highlight a point here, and you can see that this is going to be at approximately 1389. And so that's about as close as we can get anyway. Obviously, this isn't perfect. You're not getting the exact point, but this is actually really close. So this is good enough. So the yield strength here, and I can just kind of move over here. So our sigma y, let's just call it yield strength. And this unit is in megapascal again. So this is equal to 1389. Because again, here at this intersection is 1389, you can see from this set. Next, we're going to determine tensile strength. Tensile strength is another strength. Sometimes people use strength interchangeably and not specify whether they're talking about yield or tensile. But the yield strength was when plastic deformation started to occur, right? So yielding, that was down here. For tensile strength, this is more of a maximum. So how much stress can this material handle before it fractures? And so that's going to be a maximum on the curve. And so I have that here roughly with the red dot. So this is the tensile strength, or the ultimate tensile strength. You might see UTS in some cases, or sigma TS or UTS. They're all the same thing, tensile strength, but it's just the maximum on the engineering stress strain curve. So you're just looking for the maximum. This is actually the most straightforward and simplest of the four properties that we're going to look at. This next part, we're going to do the tensile strength. And when I was going through the slides on this, I mentioned this is actually the easiest part. And it's the easiest because it's just the maximum, right? It's the maximum on the curve. And so if you're not familiar with this, there is a max function. And so what we can do is we can just take the max, and you can just select the entire engineering stress column. And we go back up, and so this is our maximum, or I'll call this the tensile strength, right? So our tensile strength is 2,780 megapascal. So again, this is megapascal. Lastly, let's look at ductility. And I'm going to show you two ways in which we can calculate ductility, depending on what information you have. And we're going to look specifically at percent elongation, because I think this is more straightforward with a tensile test and the engineering stress strain curve. So let's first look at our equation. So percent elongation, or percent EL, is our measure of ductility, and it's the final length, LF, and the original length that we've already defined over the original length. And since this is a percent, don't forget the 100 to multiply this by 100. So going back to our original dog bone, we have the original length, L naught, and after the test, we can measure the final length, right? So this method implies that you have access to the dog bone. So if this is some type of book problem or so forth, then you might not have access to that. So stay tuned for the next part. But for this, if we have access to the dog bone, we're going to gently put these pieces back together. So this is our fracture surface. You see the necking that's happened here. And we're going to measure the distance between those dots, so the gauge length after the test. So that would be LF. So those are the only things we need to know, the original length and the final length, and we can calculate the ductility. So just want to make one thing clear on this. So this is percent elongation specifically after fracture, because it's taken after fracture. So this next part, I'm going to show you a slightly different approach for percent elongation based on whether or not you have the sample. So let's say that you do not have access to the sample. So this might be the case in a book problem. So our percent elongation, we can get a version of this from the engineering stress strain curve. So here I've rearranged or written this equation in a slightly different way, but this is with the recognition that percent elongation, that form of the equation in the previous slide, was effectively strain. That's all it was. It was strain multiplied by 100. But the only difference is that it was the strain at the final or at fracture, right? So that is the fracture strain multiplied by 100. So we've just rearranged it because if we look at an engineering stress strain curve now, then we can calculate ductility directly by calculating the strain. And so here we're going to do it at the point of fracture. So at this blue X that we see here. So if we take the strain value at that point, that is going to be our epsilon F, or strain at fracture. And so all we'd have to do is plug that in, and we would have a percent elongation. Again, though, I want to be clear here. This is the percent elongation at fracture, right? So right at the point of fracture. You might recall, or I'll have a follow-up video that talks more about this, but there is this thing called the elastic recovery. So when the sample breaks, that elastic energy that you put into it, that's the elastic portion here, is recovered. So you get an elastic recovery. So what that looks like is instead of going straight down, right, being at that point on the curve, it actually rebounds a little bit back here somewhere. So that's why we have to make this distinction between at and after, because the method we used on the previous slide is going to give you a slightly smaller value than what we have here. So those can be kind of small, but in some cases where we have a large elastic portion, that might be more substantial. So you just want to make sure that you specify which one. And if you're looking at other values, you might try to figure out which one they're using. Most likely, they're going to use the previous version where we take the final sample dimensions instead of use this method. So I do also want to just specify, we're not going to talk about it in this video, but we could go ahead and calculate what that would look like after the elastic recovery, right? So we could do the same thing we did with the offset method, where we make a line here and it goes back to here, and we could calculate that for what the percent elongation would be after fracture, predicting that elastic recovery. But again, it's still an approximation, and that's beyond the scope of what we have here. So the last one that we're going to work on is ductility. So we're going to kind of reset this graph. So let's reset this and reset this to 0, just so it doesn't give us anything. So resetting this graph. And what we want to do, again, for the ductility is, let's assume we don't have access to the original sample. I don't actually remember recording this one, so this is a good example. I have my original length here, but I don't have my final after the test because that data is gone. So let's use the method of the engineering stress strain curve to calculate the ductility, or the percent elongation. All right, so again, all we have to do is take that final point, and so we can go again back to this column. So this is our engineering strain, and all we need to do is go to that final point. So you'll see that the final point is this, and we just copy the value, copy it. I'm going to write it down just so I don't forget, just in case. So that is my final engineering strain. And so my percent elongation, sorry about that. So I'm going to come back over here. So my engineering strain at fracture was the value I just got. And so I'm going to paste special. I'm just going to paste the text. So this is just the value. So to get percent elongation at fracture, all you have to do is take this and divide by, or multiply by 100. So that gives us a percent. So the ductility is approximately 9%, right? So that's what this tells us, because again, we're just taking this at fracture. Again, just to keep in mind that this will change if we look at the final dimensions, right? Because the elastic recovery. So you can kind of predict, based on the slope we have over here, that the after the elastic recovery, we might be closer to this. So our ductility after fracture might be something like 8%, right? Just because of this difference in the elastic recovery. But again, the way I've done it here, I'm going to determine this. So just to wrap up here, let's go through all those values that we got. So we had the elastic modulus, and I put that down here, right? So we're just going to kind of sum up everything here. I should have pasted special and just do the values. Let's do that again. Okay, so there we go. My elastic modulus is determined to be 185. My yield strength, you can see up there. So sigma y is this, and that is megapascal. My tensile strength, or I'm going to call it UTS, it's the same thing, right? That is this quantity over here, because I've done it all over the place. And this is also in megapascal. And finally, my percent elongation at fracture is this one up here, and that's a percent, right? So there's no actual units to that. And so I can also just, it's important to keep in mind that not all these are significant. So I usually just like to report this to the nearest whole digit. And so same thing here, maybe let's do 2. That seems fine. So again, as a summary for this 4140 steel, for this test that we've done, determined from this using Excel, our elastic modulus is 185 gigapascals. Our yield strength is 1839 megapascals. Our tensile strength is 2078. And our percent elongation at fracture, or our measure of our ductility, is 9.1%. So hopefully this helps going through what the definitions for these terms and how we determine and plot the engineering stress strain, and then how we determine these common 4 properties of a material using Excel.